Thank you very much for the invitation. This is my second time presenting here, and I appreciate the time to be here. I hope you indulge my English this morning, and we're going to talk about something a little bit different, but very closely related to high-performance computing. First, I would like to take the opportunity to remind you that I come from Argonne National Lab, which is actually named after an area in France. It was a custom in the United States to name some of the forested areas after important battles from World War I and World War II. And actually, Argonne was named after an area in France. And then when the laboratory was created, it kept that name. So it's fun being here. Argonne National Laboratory has this wonderful forested campus. I'm in the building down here at the very bottom, and you can see the APS up at the top. That's the light source. It's a very nice place to visit. Maybe the food's not as good, but it's very fun to visit. And I encourage you, if you haven't been there, to come visit us and collaborate with us. Normally, I am speaking about exascale and supercomputers. That's my day job. That's what I do most of the time. And I work in an area of operating systems and system software, and have worked with Jack Dangera and Mark and others on BDEC, big data and extreme computing, and how these look for the future. However, today, I'm going to talk about something different, which is the emergence of new kinds of computing, places where computing is being applied, parallel computation, and lightweight sensors. So at Argonne, we're very familiar with deploying tremendous big sensors. So Argonne runs a project called ARM, A-R-M, and it is the project that measures atmospheric conditions and temperature, carbon dioxide, and it's the basis by which the climate models are run. So the reference data from very large instruments like this. We have instruments in Alaska, on a ship that goes between California and Hawaii, in the Azores, many places around the world. There are these very large, extremely expensive devices which measure only several data points across the world. Maybe a couple dozen is really all that gets measured. And it's very precise, but it's used for climate models. So they're big, they're expensive, they're very precise, but they're sparse. There's only a handful of them around the world. At the other end of the spectrum has been this push in very, very lightweight sensors, the kind of sensors that everyone has on their wrist or on their phone or in their shoes even, right? And these are very lightweight, battery-powered sensors. And the problem is that they're very small. That's a good thing. It's not a problem. But they're cheap. They're imprecise, but we get a very good dense spread of data, but it's not very precise. And it's used across cities, across countries, in very many places, and in the sort of the measured human, where we're understanding our own performance. However, in the United States, there's a children's story called Goldilocks and the Three Bears. And in the Goldilocks and the Three Bears, and I think there's a French version as well, I think in the French version, Goldilocks goes out to collect blackberries to make a tart. I think in the U.S. they make macaroni and cheese. But in the story, Goldilocks is always presented with something that's either too big or too hard or too small or too soft, instead of the just right in the middle. And so we at Argonne have started this project with this concept that, yes, there are these multi-million-dollar sensors, these very large sensors that we only have a handful around the world. There are also this proliferation of very, very small sensors that go in watches and everything else. But is there a just right, something that's a little bit bigger and more precise, but also has embedded computing, so we can do analysis at the edge, at the point where the data is collected? And so that leads us to this platform that we've built at Argonne, and I'm going to dive into it a bit. And it combines three pieces that we believe are very important for the future of these just right, these middle-sized sensors. So the first is that the sensor has significant computational power. And the package I'm going to be talking about today has 12 ARM cores and a GPU. So it's not a lightweight microprocessor, but we intend to do real deep learning and machine learning and actual computation on the device. The second is that there's kind of a Moore's law happening right now with sensors. It is a rapid, amazing a world where nanotechnology, MEMS, carbon nanotubes, microfluidics, all of these technologies are giving us new kinds of sensors that are extremely cheap, like 25 cents, 30 cents, $1, $2, yet extremely accurate. So this new sensor revolution can be leveraged with computing, parallel computing, and doing edge computing, and then the revolution we already know about, which is low-power CPUs, right? That's where all supercomputing, where all parallel computing is going, is to lower power, in some cases simplified designs for the CPU. Now, I was the director of the Supercomputer Center at Argonne when we were deploying Blue Gene P and when we designed Blue Gene Q. And you can see the progression. Here's on my desk. This is what the standard node looks like, Blue Gene P, Blue Gene Q. And on the right is one of these very standard now single board computers that has a Samsung-like smartphone CPU. And the capability of these CPUs, and if we look now even at the newest ones from NVIDIA, they have a developer's board called the TX1, which is designed for exactly this kind of processing at the edge. We see that computation is now available for these kind of sensing platforms at the edge. So our goal, our effort then, is to create a package of computing, embedded computing, and sensors that can go together. And so what we have here on the far right is a board which can operate and run the computers, sort of the management console for a system which runs Linux. It runs on a couple different boards and supports embedded computing. So I've brought along some of the pieces, and I'll leave them up here for people to take a look at. But here they are sort of laid out on my desk at work, and we see here the kinds of pieces that we're talking about as we build up essentially a computer in a box. So one of the things I mentioned in the other slide was a management console. So it turns out that if you want to run, as you know, if you want to run parallel computation on a state-of-the-art processor, things happen. Software breaks, the kernel can panic, you can get hardware errors, software errors. So it's really necessary in our design, since we are not in a machine room where we have a console and a system administrator running the system, we're deploying these in remote locations, we need to be able to manage them remotely. So we've built a management console that's essentially a microprocessor that's always on, that can turn on and off individual CPUs and individual boards. And so that's what the management console does. We also have the ability to pull these new sensors that I mentioned and integrate them quickly. So I'll show you one of the examples here. And there's I think later I'll have a close-up picture of this. But this is a experimental sensor board built by Intel and a company called Spec Sensors. And I'm going to open it up here so you can see the inside. It's the one that's on the middle, on the far right. You can see it there. And each one of these black dots, essentially here, these black pieces, is a printed version, a silicon printed version of a electrochemical sensor. So this is that new technology that's so cheap, for tens of dollars they can print one of these sensors, and these sensors measure things like carbon monoxide, nitrogen dioxide, hydrogen sulfide, ozone, total reducing gases. And so now we get a very interesting picture of the atmosphere, again, using this disruptive new sensor technology that we then want to partner and connect to computing platforms that are out on the edge. So if we take all the sensors and stick them together into one package, there's a piece of aluminum here where we've connected all the sensors together, then we get this sensor pod, this stalk here that includes an atmospheric chemical sensors as well as a particle sensor up at the top. That black box at the very top is something that has a laser, and it is able to look at different size particles and put them into bins. As you know, quality of life is very important based on both what we breathe and the particles that are in what we breathe and how big they are. The size is quite important for human health. So that package has been put into a unit that we can deploy in the city of Chicago. And this is going to be kind of like one of those cooking shows where now I reach below the table and pull out the final cooking product. So this, if we bake all of those pieces together, this is what we have. So this is the unit then, which has this sensor pod in this plastic piece right here. This is a injection molded plastic. So a company made a mold, and we're able to print these, and then they're all identical, so we can make this as long as we want or add more sensors. And included in this package here is the CPU box. So right here is the box that includes the CPU, and this is that box opened up. Now, it's, as I mentioned, it's a real CPU, so there's no way for us to have a fan because we've sealed the box. So we designed a special mechanism that lets us, you see the big aluminum heatsink at the top, so that aluminum heatsink connects to the box, and the entire chassis becomes the heatsink. And this chassis is then bolted onto a traffic signal pole, and so the entire traffic signal pole becomes the heatsink. So we have plenty of space for thermal dissipation. But the other key part that we want to be able to do is use the onboard computing. And that onboard computing is what we're doing with processing images here. There's a camera. And there's also a camera facing straight up to the sky. So the climate scientists are very interested in looking at cloud patterns and understanding exactly what's happening as we get certain weather conditions. So there's a set of sensors at the top looking straight up that measure infrared, ultraviolet, ambient light, and take pictures, which are then analyzed for certain cloud patterns. Now, because we're processing the images in situ at the edge with the parallel algorithms using OpenCV, we can then have a device which keeps the data local and solves some of the privacy problems that people are concerned about with having cameras and computer algorithms somewhere. So the next picture I have is a picture from one of the cameras in Chicago. We have this mounted on poles in Chicago now. However, because we have a privacy policy, I can't show you the exact picture because the point is that we're not taking pictures and sharing them with everyone. So this is the picture put through a filter that gives you a oil painting. So this is the oil painting version of what a camera in Chicago sees. And so we're looking down from an intersection, and we can process in the parallel computer, so in this 4-processor, 8-processor with GPU computer, we can do computation to look at cars, pedestrians, bicycles, people, how many people are pushing strollers, what time of day, do we have near collisions. There's a amazing range of the kinds of questions that people want to ask by doing algorithms in situ at the edge. So one example that has come up already is in Chicago. It might be different here, but in Chicago, you can imagine looking down from an intersection and seeing that a car pulls up to the place where you're supposed to stop. Often there's a white line there called the stop line, and the cars pull up like this every day. You can see them pulling up like this. There's a certain sort of average that gets built. And then one day, while the computer is looking at those pictures, cars beginning to come forward and turn as they get to the stop line. Well, in Chicago, that's because the road is icy, because there's been snow. So you can already imagine an algorithm that automatically detects when an intersection is becoming dangerous and either deploying more trucks to put salt or changing the timing in the lights to add more yellow light. So these kind of algorithms is really, that's the limit. It's open for us, for the community, because this is an experimental process. The city of Chicago is letting us put 500 of these in Chicago, and they can be accessed by computer scientists to write these kind of algorithms. So there's a whole set of things that people have already come up with. For example, can we imagine being able to determine what's called a near miss? When have pedestrians, had to run back because a car goes through an intersection? How often are bicycles and cars and people really having problems in an intersection? Right? Even before there's an accident, what kind of indicators can we have? So the algorithms that are being used that are already available are things like OpenCV and Cafe. I had a grad student working on this for me from Caltech, and I made a reference to being able to pick pedestrians out like, Abbey Road, and he had never heard of that before. So he had to go look on the web, and so then he ran the Wikipedia picture of the album through the software, and you can see that it picks out what people are, right? It can classify people. These are standard algorithms, and it can classify even that, I guess, 1960s Beetle in the back there as a vehicle. And so these algorithms are the same kinds of algorithms that are being used in self-driving cars and in other autonomous vehicles. And we're going to see an explosion in high-performance computing in this space, edge computing, where we're processing things at the edge, and parallel computing. These two things are coming together. When a self-driving car is navigating, it's not using its cameras, taking all of those pictures and sending it up to the cloud in order to find out where to drive, left or right. That's all handled locally within the device. And so as sensors and infrastructure becomes smart, we'll have parallel computers, not just 4-processor or 8-processor, but you can imagine 32, 64. You can just keep scaling up as we scale up with what kind of computation can be done at the edge. Now, when we talk to scientists, there are a wide range of things that they want to do with computer and with audio. We also have a microphone with vision and with audio. So, of course, looking up at the sky is a good example. Over on the bottom right is a picture of a river, and you can see in the middle there on the bridge there's a white stick with some red marks. It's kind of hard to see right to the left of the yellow sign. That's a very classic way in which today people look at rivers, and I know when there were floods in Paris, you're measuring by the statue, how high the water goes on the statue, right? So these kinds of things can be picked out with a computer program running in parallel quite easily. What is the water level? Is the water level have ice? What's the rate at which it's moving? And building a hydrological map of the city is very important for Chicago. The top middle picture with the water on the street, West Chicago floods, and it's quite damaging because the floods cause water from the sewer to come into people's homes in the basement. This is not attractive. Very much a problem. But the city has no model to understand what is the flooding and how. They could try and put sensors everywhere in the city, or with the right kind of image processing, you can see the standing water. You and I can see the standing water on the street. it's very easy for us to imagine a computer program that tells us how much standing water is beginning to accumulate in roads and use that to calculate where is flood going to happen, what should the city be doing. Sometimes it's as simple as a blocked drain, right? So it just needs to be cleaned out. But these kinds of things are all vision-based things. Up on the right is a picture of a frog. There's a group at a forest preserve that has a species of frog that only makes sound 2 nights every year. So everything that they need to do that's important happens during those 2 nights. And so hearing that sound during those 2 nights would be very helpful, and processing it and automatically knowing, oh, tonight you should go out because this is the time to take the measurements and to understand the frog population. These are all things that can be done with processing at the edge. So we've built these units and we've tested them at Argonne, and we're beginning to deploy them. We have tested for the FCC to make sure that they can be deployed outside in a standard urban environment. And we're beginning to get back data from these. We have several of these deployed in Chicago, and I'll show you some pictures. And we're deploying them also in a prairie. We also have some deployed in Chattanooga, Tennessee, where they're doing measurements of pollen and comparing the measurements from the particle sensor with predictions using big data to predict when asthma attacks will occur. And this is actually very important for school systems. There's a lot of absentee, a lot of kids are missing because of respiratory problems in schools, and knowing ahead of time what day there might be a difficult problem with pollen, kids can ride the bus or take a car instead of walk. So these are the kinds of problems that people are looking at. So we have a platform, and it's an open platform for research. It's all open source. The hardware is also available and open. It does computer vision and tries to integrate the latest sensors, and it's very easy to integrate your own sensors because it's all an open source platform with serial lines and USB and Ethernet and so forth. And it takes advantage of these small parallel computers for smartphones and so forth. So the project in Chicago is one example of using the platform. And I have just a couple minutes left. I'll tell you a little bit about the project in Chicago, although the platform is open to be used in other ways. We happen to fit it into this for Chicago, but it can be used in other research projects. So the research project in Chicago is part of a National Science Foundation grant to build an instrument to measure Chicago and to allow scientists to add their own instruments to the city. One of the impediments, if you are a scientist and you're working on a new sensor, there's really no way for you to get that tested in a city. You know, let's say you build a new particle sensor, and we're working with someone from University of Illinois in Chicago who has built a new MEMS particle sensor that's very inexpensive. But if you were going to try and deploy that yourself, you'd have to try and get permission from the city, and of course the lawyers are involved, and then nothing happens, and it never moves forward. So the NSF has designed this project so that the entire project is a laboratory in Chicago. There will be 500 nodes as part of the laboratory, and scientists can ask to have their node added, their sensor added to nodes, also run their own algorithms to do vision and audio processing in the box. So this is a picture from a little bit far away from the Chicago campus. This is the University of Chicago campus, and we're looking up north along the river to the skyscrapers of the city, and that's where the first units have been deployed. One of the questions that people ask is why are we so fixated on cities? It turns out that cities represent about 70% of greenhouse gases, 70% of the energy, and 80% of GDP. And if you look at all of the trends for China and Asia and everywhere else, even in Europe, people are moving into cities and away from rural areas. And so instrumenting and understanding cities is a very key part for science to understand what's happening and how to improve quality of life. An example here in Chicago is looking at life expectancy. So if you look at the left-hand map, you see life expectancy in the city, and you can see very clearly there are areas where your life expectancy, especially from health-related things, is quite low. And if you look at the right, that map is asthma, right, and prevalence of asthma. And you can see how these things are related, but are they related for socioeconomic reasons? In other words, access to health care. Maybe that's the reason they're related. Or maybe it's related because the conditions are actually different, that there's actually bad manufacturing and air quality in some of these areas. In order to differentiate those two, we really need very good block-by-block sensor data in order to compare. So the project is to deploy air quality and these cameras and audio and to deploy these across the city and to build a network where people can explore the data. The data is all open, but can also look and add their own algorithms to look at what's happening in intersections, what's happening in parks, and so forth. As I mentioned, the nodes have already been going up in Chicago. You can see on the far right at the upper right-hand corner, they're preparing one of the nodes which will go up on a bucket truck, which you can see in this middle picture here. They go up and they drill a hole in the traffic signal. They mount the device with some stainless steel bands, and they run a power cable down, and it connects up to a standard 10-amp breaker. And then we have an AT&T cell phone modem, and it immediately starts transmitting, and we're online. And so all of that data then goes back to a repository, and it's made available. And as I mentioned, the kinds of things that people are imagining are being able to write their own apps for that data. So to tap into that data stream and immediately look and say, okay, well, can we determine a hazardous condition? Can we determine what kinds of action should be taken, whether it's salt for trucks and cleaning up intersections, or maybe an alert because a certain area has gotten too high with respect to ozone or particles. So that's the kind of interaction that the city expects. As scientists, we have climate scientists and health scientists and others looking broadly across all of the data, wanting to understand how it relates to weather patterns and climate. Right now, you might know that climate models generally model the city as a large rock. It's simply a big piece of cement for a climate model, and there's a heat island effect which says, okay, the city is a big hot rock, and during the day you warm it up, and at night it gives off heat. And that's roughly the extent of how we understand cities in climate models, maybe a little bit better than that, but not a lot. But there's a lot of things going on in a city. So, for example, at about 5 or 6 o'clock, everyone goes home to make dinner, and they turn on their natural gas, and they start, in apartments everywhere, start emitting carbon dioxide. And so the rate of carbon dioxide, both from cooking and then the rate of pollutants or the release of pollutants from cars, is cyclic and has certain patterns in certain parts of the city. And those patterns may be quite important in modeling and understanding the city as well as quality of life. But we really don't have much instrumentation. We only have 1 or 2 sensors. In the United States, the Environmental Protection Agency maintains maybe 5 or 6 sensors in all of Chicago, which is millions of people, and they maintain a handful of sensors, and that's really it. So in order to understand this data more exhaustively, we really need edge. We need computing and better sensors all the way at the edge. The lab has been working on educating local schools and working directly with local schools. Of course, one of the issues whenever you introduce new technology is people have a little bit of maybe fear, a little bit of resistance, like, okay, well, who's putting that on the pole? What's it do? Why? And so we found that it's very important to start outreach immediately with schools and explain sensors, allow people to use Arduinos and code up and write their own little programs and add sensors to a package to do that kind of hands-on work in schools so that people understand how we are instrumenting the city. The project has already has a number of partners that are very, very interested in deploying around the country and around the world. We are, of course, in Chicago, but places like Seattle and Portland, also Newcastle and Bristol in the UK have signed up to deploy nodes immediately. We're talking, of course, with Francois about ideas for deploying technology and deploying sensors here in France. About a month ago, I was in Delhi, and they're very interested, especially countries that have air pollution problems. This is quite important to understand. And there's a new dynamic that I really hadn't, I wasn't thinking about when we were working on this project. I don't know if you know, in the United States, there was a very bad situation in Flint, Michigan, where there was lead in the water. And the local municipality, of course, struggled to understand what's happening, and there's a lot of blame with respect to when did the city know and what did the city do about the pollutants that were in the water. And it turns out that there was a group at Virginia Tech who were measuring the water and providing scientific data about what they found in the water as an independent university providing that data. And so when we go to some of the countries, the idea that a university instruments the city and provides data on quality of life, and whether that's air quality or particulates or even traffic, the idea that an independent university or laboratory provide that data is very appealing. And I hadn't quite really understood how important that is from that perspective, that there's a way for science to come forward and provide data, not just the city, but external science groups represented in universities around the world. So let me wrap up now with a slide that says, well, okay, this talk was a little bit different than standard HPC and big data. I understand that. But why should HPC folks care? Why should we be interested? Well, the first thing is that everything that we know about computing and supercomputing is being miniaturized. It's being put into units like this. So OpenCL, OpenMP, all the pieces that we know about with resilience. You can even imagine that someday this is going to be running MPI, right? It's not yet, but that's the kind of world that we're headed to, where there's real computation at the edge. So we should be involved in that and start working on the programming models for that right now. There's also that data reduction that happens, and instruments, this is a kind of instrument, needs to be able to reduce the data as it flows through. We don't, even if we could, for privacy reasons, the volume of data that we can collect at the sensor it's not possible to send all of that back to the cloud, right? There's just too much data. So we need to do reduction right there. The idea that we need to make a new programming model that allows stackable analysis. That's something that's we don't have right now, and we're struggling with. How do we do an analyze for cars and pedestrians and wildlife, and without making just a copy of the data and running each pipeline independently? We really need a way to stack that up in an analysis pipeline. Of course, this makes a perfect distributed instrument, and so there's a programming model question. There are management questions with respect to that. There's also great questions about how we trigger high-performance computing computation. the climate scientists and the weather scientists really like the idea of getting live data from a very large 500 sensor grid on Chicago, and then being able to fire off HPC computation directly from the data. So that you get the last hour of data up to the minute and then run the next simulation. So that kind of streaming of high performance computing based off of instrument data is something that's very attractive for scientists at Argonne. Of course, there's also an architecture issue. Right now we're using smartphone technology. We're using just a couple, 4 and 8 core ARMS chips. But clearly we should be looking toward even lower power and higher computation, and that can mean interesting new architectures. It could be FPGA architectures, the sort of neuromorphic ideas where you might do the neural net things that Caffe does, or TensorFlow, do that in the edge. So these are all ideas open, and they're part of HPC. We're already, of course, in HPC looking at how do we use Caffe, TensorFlow, neural networks, and machine learning, and how do we push that to the edge. So this is very natural for this community. So with that, I'll have time for questions, and
thank you very much, Pete.
thank you.
Hi, so first question is, what's the price of the device?
Yes, so the computer parts here are actually fairly inexpensive. The boards here end up being, a couple $100s. Once we add manufacturing and having this all put together into that, it means that the node itself is a couple $1,000s. Now that's actually a good thing, and I'll explain. So this part of this Goldilocks of how big should it be and how expensive should it be comes down to how much does it cost to install. So you saw that bucket truck that lifts a guy up to drill a hole. It turns out that it's probably $2,000 or $3,000 for the city to do that installation, and they're paying for that. So that the science project doesn't have to pay for that. The city pays for that. So the cost of a unit that we should put up needs to be amortized based on the install cost. So we're trying to target adding enough sensors to make it in the $3,000 to $5,000 range, just for that to make sense for the city, so that the city will do it. Okay. For experimentation in laboratories, it would be half that, because it's just computer parts. Yeah.
Okay, so it's quite expensive. So your goal is just cities. You don't expect to give it to people, so people can have it wherever they want, and then after you can use the data, since it's open data.
No, so we have two projects. It's a good question. We have two projects going on. So one is to build this unit here, and the other is just the open platform part, and that's being deployed by people in other projects. So we have one project that's instrumenting a prairie, a grassy area near the city, and they're adding solar panels so that they can instrument without power, so they can instrument the prairie and send the data up. We also have another group that has the sensor boards and are putting them in New York City in advertising kiosks, turning those advertising kiosks into things that also measure the air quality. And so the technology and the platform is open. That's the part that's, that scientists are going to use for other projects. The pollen project is an example of that up on the roof. It's just it's in a white box, big ugly, we call it the ugly box, big white box. And that's one use of the technology, and that's open for everyone, and all of that data is shared into one repository so that everyone can look at the data. So the data from Tennessee, from Chattanooga, and the data from the prairie also is combined with the data from these so that everyone can look at the data.